what we did the other day was factored quadratic trinomials. This is not a quadratic trinomial. You notice the power on this is w to the fourth power. This is actually a quartic equation. You don't have to know that yet, but you do need to know it's not really quadratic. Although it does kind of look quadratic. And let me point out why this kind of looks quadratic. You have a fourth, instead of second, first, and zero power, you have a fourth, second, and zero power. The first power is double the second power. Anytime you have this sort of situation happening, you can factor it as if it were quadratic. Except for when you have your parentheses, instead of w and w, multiplying to give you w to the fourth would be a w squared and a w squared. And again, anytime you have a double power, anytime this power is double this power and then you have no variables at the end, treat it as if it were quadratic. Ask yourself what adds to give you negative 6, multiplies to give you negative 16. What would those numbers be, Trevor? Good job. So it'd be a negative 8, positive 2. Any questions there? Now, from here on out, something else we need to start looking at. See if there's any further. See if you can go another step. Okay, we factored this into two different things. Now let's see. Okay, this is not a line. Okay, w squared minus 8, that's not linear. W squared plus 2, that's not linear. See if you can go further. Since there's two terms, you can look at that list we made out the other day. Anytime you have two terms, check to see if it's difference of squares. Check to see if it's difference of sum of cubes. If it's not, you can't do anything else with it. Okay. Is w squared a perfect squared? Yes. Is 8 a perfect squared? No. Okay, so not a whole lot you can do with it. So we'll leave it as if. Now w squared plus 2, obviously that's not difference of squares. It's not even a difference, it's a plus. Now let me show you something. You could, you don't have to on this, but you kind of could factor w squared minus 8. WW plus minus factors into conjugates, right? And even though 8 is not a perfect square, it's not like 9, 3 times 3. It's not like 16, 4 times 4. Anybody tell me what multiplies to give you 8? And like I said, this, you can factor, but you can't because it's not going to come out very nice and neat. What multiplies to give you 8? Somewhere between 2 and 3, right? How do you find out what two things multiply to give you 8? Square root it, right? So could I factor this into w plus the square root of 8 and w minus square root of 8? Could. Try to multiply that out. It's conjugates. W times w is w squared. Positive root 8, negative root 8. What is square root of 8 times square root of 8? 8. Okay. So it's not the nice, neat factoring that you're used to seeing, but you could do that. Next one. This is not quadratic, but it's quadratic in form. Stuff squared plus 7 times stuff. This is just like x squared plus 7x plus 12. Right? To where in the place of x, you have a squared minus 3. And what I'm going to do here is we're going to make a substitution, and I'm going to say that I'm going to take out this a squared minus 3 just because it's confusing looking. And I'm going to say take out the a squared minus 3, replace it with x, and let's factor it like that. Okay. Instead of stuff squared plus 7 times stuff plus 12, we now have your stuff as x. Now let's factor there. Savannah, x squared plus 7x plus 12. Adds to give me 7, multiplies to give me 12. What do you get? Good. And we don't circle that. Your original problem was a squared minus 3 squared, not x. Okay. We took out the a squared minus 3, put in x. Why is that legal? Because I'm about to turn right around and put that a squared minus 3 back in. Okay. I did that first step just to simplify things a little bit, just to make it look better. But now once you get to here, let's say, okay, now instead of x, put it back in. So we have a squared minus 3 plus 3. and we have a squared minus 3 plus 4, which will be just plain a squared times a squared plus 1. That's factoring by substituting. And that's always legal. If you've got any type problem, if you've got a minus 3s across the board, you've got several of them in a problem, and you want to take them out and just put a plain x in there, that's legal. As long as at the end you substitute back in. Okay, if you want to clean anything up that has multiples of the exact same thing, take them out. Put in a different variable for them, solve it that way, and then plug back in at the end. So if what's another way I could have worked this? Could I square this out? Could I distribute this, combine like terms? Sure. Would you get the same answer? Yes. Okay. Factoring completely. Going through again, reviewing your steps of factoring. Step number 1, always see if there's anything you can factor out. See if there's any common factors. Step number 2, look and see how many terms there are. If there's 2 terms, check to see if it's difference of squares or difference of sum of cubes. If there's 3 terms, see if it's a quadratic trinomial. Can I factor it to see what adds to give me the middle term, multiplies to give me the last term, or bottoms up? If there's four terms or more, try factoring by grouping. Now this one, 2w to the 4th minus 32. Elizabeth, 2 and 32. Do you see anything in common there? Good. There's no w's in common because we just have a w here, but we do have a 2 in common. Good job. We ask ourselves 2 times what gives me 2w to the 4th, which would be w to the 4th. And 2 times what gives me minus 32 would be minus 16. It's a good problem. This will probably end up on your test. This won't factor anymore. Why? It's a number. This will. W to the 4th minus 16. Go through your steps. It has 2 terms, so we say, is it difference of squares or difference of sum of cubes? And yes, it is. 2 sets of parentheses. Difference of squares factors into the square root, w squared, plus and minus. What goes next, Brett? Plus and minus what? Good. Are we done? Still w squared, isn't it? If at all possible, when you're factoring, if at all possible, you want to keep going until you have w to the 1st. If possible. W squared plus 4. 2 terms. Can we break it down any further? No. So we leave the 2. We leave w squared plus 4. We can do something with the other one, though. W squared minus 4. Avery, what will that factor into? WW plus and minus 2. Again, difference of squares always factors into conjugates. You got 2 lines out of it. Again, if you can factor down to all just w to the 1st stuff, awesome. But here you have w to the 1st here, but you got parabola here, you got w squared. We did it as far as we could. Next problem, again, always find common factors first. Logan, what's in common? And good, 6 and x. And I'm going to go a step further. I'm actually going to factor that negative out with it. Reason being, I really don't like a negative to be your leading coefficient. So if I've got a negative out front, I'll usually go ahead and factor it out as well. You can do it either way. Negative 6x times, okay, negative 6 times 1 gives you negative 6. X times x to the 6th gives you x to the 7th. Negative 6 times negative 1 gives you positive 6x. There's step 1. I'd start this one. This is a good one. Okay, this is linear now. It's x to the 1st power, but this is not. X to the 6th. Let's see if we can go further with it. Question. Since it has 2 terms, we're going to check to see if it's difference of squares, or we're going to check to see if it's difference of sum of cubes. Is that difference of squares, or is that difference of cubes? It's a trick question. Cube sounds good. Anybody want to go with squares? It's both. And you can solve it either way you want to. Okay, You can either go ahead and factor it like difference of cubes first, or you can factor difference of cubes second. Because look what's going to happen. Here you go. We got negative 6x. Two sets of parentheses. X to the what power, anybody? What multipliers give you x to the 6? X to the good, third. Multipliers give you negative 1 will be a positive 1 and a negative 1. Ooh, this one's next. Okay, so we factor difference of squares. And like I said, I'd star this one because, look, you're nearly going to use every type of factoring on this problem. Step number 1, we factored out a common factor. Step number 2, we did difference of squares. Step number 3, this one's an obvious difference of cubes. X to the third plus 1, x to the third minus 1. Well, it's an obvious sum of cubes and difference of cubes. Let me get my formula here. Edit. There's my formula. Let's do x to the third plus 1. That's kind of obvious what your a and b are. Your a is x, and your b is 1. So everywhere you have an a, put an x. Everywhere you have a b, put a 1. So that's going to be x plus 1 times x squared minus x plus 1. That's factored there. Now let's factor x to the third minus 1, which will be, again, your a, in place of your a is an x, in place of your b is a 1, so that'd be x minus 1 times x squared plus x plus 1. And I promise that's as far as it's going to factor. This x squared, you can try again, this x squared stuff. You could say what adds to give me negative 1 multiplies to give me positive 1 doesn't exist. What adds to give me positive 1 multiplies to give me positive 1 doesn't exist. That's as far as it'll go. If it did exist, guys, if it would break down again, this whole difference of sum of cubes, if it break it down again, they wouldn't have the formula as this. Okay, it would keep going. But I promise, once you break down using these formulas, that's as far as it'll go. Up to this point, we have factors from x to the fourth. I did one problem a while ago to where it kind of looked quadratic, and we could use kind of the quadratic method to factor it, but this one's not at all quadratic. So what we're going to do, and the only way we can factor these is right now is as they're giving it to us. It says factor this completely given that x minus 2 is a factor. Here's what I want you to do for review. Divide it. If something's a factor, let's say I know that 2 is a factor of 16. So since 2 is a factor of 16, when I divide it and get 8, that means I could take 16 and I could break it into 2 times 8. That's factoring. What I want you to do is take this problem, factor this given that x minus 2 is a factor. Use synthetic division. I'll give you a second to try it on your own. Use synthetic division to divide this into x to the third minus 7x plus 6. Okay, just tell me with the setup of it. Hang on just a second. Allie, what goes in the box? If you're dividing by x minus 2, you're going to put a 2 in the box. Now, can somebody tell me why most people missed this problem? They didn't put a 0. Should I put a 0? 1x to the third, 0x squared, negative 7x plus 6. Most people will miss this problem because they did not put the 0. Okay, let's go through and actually divide this now. Bring down the 1, and then you start multiplying by what's in the box. 2 times 1 is 2. Add these together, multiply by what's in the box. Add these together, multiply by what's in the box. Add those together. If you didn't get a 0 there, they were lying to you. It says it's a factor. Why is 2 a factor of 16? Because it'll divide into it. Why is 9 a factor of 81? Because it'll divide into it. If this is truly a factor, it must divide into it with no remainder. So here we go. Let me remind you what I just did. I just divided x minus 2 into x to the third minus 7x plus 6. And I got, this is a constant, this is an x term, and this is an x squared term. So I got x squared plus 2x minus 3. What does that mean? That means I just factored that x to the third minus 7x plus 6. I can now rewrite x to the third minus 7x, and get used to this, you're going to do a lot of this. X to the third minus 7x plus 6 is equal to x minus 2 times x squared plus 2x minus 3. So let's factor completely. Okay, I just went from x to the third stuff to x times x squared stuff. Okay, I broke it down first step. But I told you, try, if at all possible, to break it down into a line times a line times a line. X to the third stuff should be 3 lines. See if we can go further. X minus 2, 2 sets of parentheses, bless you. X times x, adds to give me adds to give me positive 2, multiplies to give me a negative 3. Lydia, does anything exist? Adds to give me positive 2, multiplies to give me negative 3. Positive 3, negative 1. Okay, next up, objective. Students will find the domain of rational expressions. They will also perform operations on rational expressions, including simplifying, multiplying, dividing, adding, subtracting. So, hey, that's pretty easy. We're just adding, subtracting, multiplying, dividing fractions. That's all we're doing. Okay, we're going to go back, we're going to review fractions. And then we will also work with what's called complex fractions. We don't call them complex because they're hard. And we also, this is weird, we don't actually call them complex because they have imaginary numbers in them. Complex fractions. Before we get started, the word domain. You will use the word domain tons in pre-calculus. A domain, and you remember back from algebra, domains and ranges, x's and y's. And that's how you were taught to remember that the domain was the x's, the range was the y's. Well, it doesn't have to be. Your domain is the set of inputs. Okay, let's talk computer now. When you have a function, okay, what you're putting into that function, which is most of the time your x value, those are your inputs. That's your domain. What you get out of it, that's your range. Your outputs are your range, your inputs are your domain. So if I ask you what's the domain, that's simply saying what all could you plug into this. Okay, most of the time it's easier to give me a list of things that you can't plug in, but sometimes it might be flip-flop. But if I ask you for domain, it's simply what can x be? What can I plug into this? So here we go. These are easy. Find the domain. The domain is simply what values can x be? A number divided by 0. Anytime you're dealing with a fraction, and you have a number divided by 0, can't do it, right? It's undefined. It says no. So in this case, if I ask you for a domain, and a lot of people will say 0, everything but 0. Can't have 0. Yeah, 0 is fine. Okay, if you plug in 0, you get 2 times 0 minus 1, that's a negative 1 on top. 0 plus 3, that's a 3 on bottom. 0 is okay to plug into. Okay, you can plug in 0, but what value can you not plug in? What value, when you plug it in, is going to give you a 0 on bottom? What do you think, Henshaw? What value will make the bottom equal to 0? Negative 3. So if I ask you for domain, again, there's a couple of ways you can do it. You can either tell me what x can be, or you can tell me what x cannot be. In this case, x cannot be negative 3. How do we find that? We say, okay, what makes x plus 3 0? We move the negative 3 over, and you get, or excuse me, move the 3 over, you do get negative 3. So your domain is, I don't care for you to just say x cannot be negative 3. We'll talk about other ways to write that later. What makes the bottom here equal to 0? Not quite so easy just to look at. And we're going to be using the stuff that we learned previously to do this. This is actually from Algebra 2. What values will make the bottom equal 0? It's a quadratic equation, right? As a reminder, to solve a quadratic equation, the ones that I'm going to give you today are pretty easy. They're going to be factorable. To solve a quadratic equation, we've got to set it equal to 0. We factor it. We ask what adds to give me 5, multiplies to give me 6. That'd be a positive 2 and a positive 3. We split it, and we say, okay, x plus 2 equals 0, x plus 3 equals 0, and we solve each, and we get negative 2, and we get negative 3. What that means is, if I plug in negative 2, if I plug in negative 3, I've got a 0 on bottom. Proof. Let's try negative 2. Negative 2 to the second power is 4. 5 times negative 2 is negative 10 plus 6. If you plug in negative 2, you get 4 minus 10 plus 6, which is 0. You cannot have a 0 on bottom. So instead of saying x is negative 2 and x is negative 3, actually let's say x cannot equal negative 2, x cannot equal negative 3. That's your domain. Next one, x squared plus 8. What makes that 0? Is it possible to plug anything into x squared plus 8 to give you 0? Why or why not? If you take x squared plus 8, square anything. Take a negative number, square it. Take a positive number, square it. You got positive. Is there any way that you could take a positive number, add 8 to it, and give you 0? Impossible. The lowest that you could actually have, you can't have a 0 on bottom, no matter what you plug in. The lowest value that you could ever have on bottom here is an 8. If you square 0 plus 8, that'd be 8. If you square anything else, square negative 1 or positive 1, you get 9. Square negative 2 or positive 2, you get 12. It goes up from there. So it is impossible to give you a 0 on bottom in the real domain. I will show you, and you don't have to put this, because here your domain, all real numbers. If you actually look at the graph of this, you can put in anything. You could actually draw this graph without lifting your pen. Okay? All real numbers. It will continue forever left and right. It doesn't look like that. But it will continue forever left and right. But there is two imaginary numbers you wouldn't be able to plug in. Let's talk about those. Just in review. Move the 8 over. You get x squared equals negative 8. And that right there, this shows you obviously that there's not going to be any zeros in the real domain. Because if you square a number, you don't get a negative. Unless you're in the imaginaries. Positive negative squared to negative 8. Which is somewhere around 2.9i or something. What you do is you split it. Let's split it into the square root of 4, times the square root of 2, times the square root of negative 1. Again, this is just all review. That'll be positive and negative 2i root 2. That would be the imaginaries that you could plug in. But as far as what is the domain and what I expect out of you for this, the domain is all real numbers, because how many times do you make a t-table and you start plugging in imaginaries? Never. Okay, you've not done it, ever. So when I ask for the domain of this, all real numbers, you can plug in anything you want to, unless you start getting a little weird on me. Okay? That's enough of those. Reducing fractions. Let's start with a tough one. 8/12. And let's remind you how to reduce fractions. Let's remind you of what you were actually doing when you reduce fractions. Okay, now that you've reduced fractions for several years now, here's what technically you were doing here. You know, teachers always told you in elementary, Find a number that will divide into both of them and just divide it. Yeah. You were actually factoring, whether you knew it or not. When you found a number that would divide into both, okay, here it's 4, right? You were actually factoring the top into 4 times 2. You were factoring the bottom into 4 times 3, right? And you were canceling the 4's out. And you were left with 2/3. So when you found a number that divided into both, in essence, you were factoring and then canceling out that factor. We're doing the same thing here. To reduce a fraction such as this, okay, please, okay, make special note of this. Whatever you do, don't start reducing like this. Don't start marking out like 4s and 6s. That's the number one mistake. Somebody will still make it, okay? You can't, they got pluses. If you're going to mark out part of a binomial or part of a polynomial, you got to mark out each part. You can't just do pieces. So how do I cancel? You factor first. The same way with reducing 8/12. Find something that divides into both of them. Well, here's how we're going to do that. We're going to factor the top, factor the bottom. This will give you extra practice with your factoring. On top, the only common factor is a 2. On bottom, you have a trinomial. It'll factor into x and x. Help me finish factoring that, Jordan. What adds to give you 5, multiplies to give you 6. Thank you. So we broke it apart the same way we did 8/12. Then we look to see, is there anything in common? Yes, top and bottom has an x plus 2. So this factors into 2 over x plus 3. I'm kind of getting ahead of myself, but I think it would be better if you saw this twice instead of just seeing it once when we actually get to it in the book. We'll talk about later on graphs of rational functions, so we're touching on this again. We're going to talk about graphs of rational functions and talk about, okay, what happens when you've got factors on the bottom or the same factor on top. And I'll go ahead and share that with you. Anytime you've got, we're fixing to graph this. Anytime something's a fact, well, look at the bottom. What's your domain? What are the two things, by looking at the bottom, what are the two things, Brianna, that x cannot be? Because it'd give you a 0 on the bottom. -3 and -2. Good job. Something special happens on your graph because you can't plug those numbers in. If you plug those numbers in, black hole, right off the bat, right? Have you ever seen that poster, black holes are where God divided by 0? Yeah, I need one of those. Hang on my wall. Those are pretty cool. But anyway, as soon as you divide by 0, bad things happen. Plugging in -3, -2 gives you zeros. Okay, so what happens on the graphs? If you've got something like -2, notice it's called removable discontinuity. I'm going to go ahead and touch on some calculus there. Removable discontinuity. Why do I call it removable? Because it actually cancels each other out. Removable discontinuity results in a hole. Not black hole, but just a hole. What does a hole look like? You've got your graph, you've got a hole, and then you got the rest of your graph. It just skips that point. Okay? Non-removable discontinuity, like x plus 3 here, results in what's called a vertical asymptote. Your graph comes along, and then bam, shoots straight up in the air. Then on the other side, your graph's coming along, bam, shoots straight down. It can't cross that line. So it'll get close to that line, but it'll never cross it. So here you have both types of discontinuity. You have a hole, and you have a vertical asymptote. But what's the relationship between this graph and this graph? It's the same graph with one exception. And I just want to touch on this, that yes, we marked that out. If you plug numbers in, you're going to get the same. You can try it. Plug in a 5. Here, plug it in here. It's the same thing. You'll get 1/4. Plug in a 5 here, you get a 4th. Plug in a 5 here, you get a 4th. The only difference between this graph and this graph is this one's going to be missing what? Does anybody notice it? This graph will not have that hole, would it? So when you have that removable discontinuity, and here's your proof. Here's the first graph, and there's that asymptote line right there. And then here comes your second graph. It's the same thing. Okay, they're identical graphs. Why are they identical graphs? Because this is equal to this. That's the whole purpose of it. You're reducing it 2/8 and 1/4. They're equal. They're the same thing. You're reducing this into something that's equal. By the way, if you do have one of these calculators, notice here. Let me show you. I'm going to plug in -2. Look what it gives you. When you plug in -2, your y value is non-existent. Now, if I go trace and I hit, I think it's down, notice what I changed to the other one. Now, if I plug in -2 there, yeah, I can plug it into that one. Plug in -2, you get 2. Can't plug it in here because of this discontinuity on bottom. You can plug it in here. That'll become valuable after Christmas when we start talking cal. Not cal, C-A-L, not C-O-W. Next one, reduce it. On top, it doesn't look factorable. On bottom, I notice difference of cubes, and that's kind of nice. It actually fits my formula perfect. They even used A's and B's. That was so nice of them. Let's go to, let me paste my formula here. So on bottom, I believe I know what that factors into. A to the third minus b to the third, difference of cubes factors into a minus b times a squared plus ab plus b squared. But the problem is you got an a minus b, but there's not an a minus b on top. You have a squared plus ab plus b squared, but you don't have the same thing on top. Nothing cancels out as of now. Showed you a trick the other day. This is not a minus b, but I could turn it into a minus b. Does anybody remember how to do that? Thank you. Factor that negative out of it. B now turns into negative b. Negative a now turns into positive a, and you can flip-flop them. Now it's a minus b. Now you can cancel them. You're left with, on top, -1. On bottom, you're left with a squared plus ab plus b squared. Just for you aspiring engineers out there, here's a tough question. What's your discontinuity there? What are some things that a and b cannot be? What values of a and b would pose problems? Because you can't have a 0 on bottom. So what's true about a and b? Here's your discontinuity on this one. A cannot be b. You don't have to put that. That's beyond. But you will have discontinuity when a and b are the same thing. And that, right there, that's what causes problems. That. A minus b. A cannot be b. A and b cannot be the same values. Okay, that's enough of that. Moving on. Reducing fractions, again, hey, we've done this. But I like to drill stuff in your head over and over and over, so let's do it again. Daniel, you've got 2 x's on top, you have 5 x's on bottom, you're left with, okay, -3 or 3 x's on bottom. And you can write that as x to the -3 on top, or you can just say, well, there's more on bottom, let's mark them out and put the answer on bottom. Colby, you've got 3 z's on top, 1 0 on bottom, you're left with 2 on top or bottom. Good. Final answer. So some of your fraction reduction will look like that. Those aren't too bad. Now let's multiply and divide fractions. Then we'll be about finished. That'll put us in a good spot. If we can finish multiplication today, we'll divide and do everything else tomorrow. How do you multiply fractions? Everybody's like, I don't know. That's the reason I'm in pre-cal. I didn't know how to multiply fractions. 2/3 times 6/7. To multiply fractions, guys, just multiply tops, multiply bottoms. That's it. Okay. If they're mixed numbers, you have to change them to improper. Multiply tops, multiply bottoms. That's all. Now, I tell my younger students, you've got an option though. You're going to have to reduce your answer. 12 over 21, divide by 3, or factor out of 3 and mark them out, whichever way you want to think of it. You've got to reduce your answer, but you've got an option. You can either reduce your answer before you start, or before you multiply, or after you multiply. We've called that our whole lives cross-canceling, but it's reducing the fraction. 2/3 will not reduce, 6/7 will not reduce. 2/7, you can also reduce in this direction. 2/7 will not reduce, 6/3 will reduce. Reduce those. And gives you, divide by 3, gives you a 2 and a 1. And then multiply. Okay? That is simply reducing before you multiply. You're doing the same thing here. You can reduce it before you multiply, or you can reduce it after you multiply. I would do it before I multiply it. First fraction, you have an x minus 1 on top. Always factor. You have an x plus 2 times x plus 2 on bottom. Notice that you come out with the same thing there. It's because half of this squared gives you that. That's a perfect square trinomial. Here you have a line on top already. Don't try to factor a line. Get bit. On bottom you have x squared plus 2x minus 3. Caleb Haynes, x and x. What multiplies to give me negative 3 adds to give me a positive 2. Give me a list of multiplies to give you 3. That'll make things a lot easier. It's a short list, right? What multiplies? I'm sorry. What multiplies give you 3? 3 and 1. That's it, right? So if 3 and 1 does not work, this is not factorable. We need to add, well, multiplying to give me a negative 3, so we know it's positive and negative. Add to give me a positive 2. That means you have $3 and you owe $1. So that would result in a positive 2. Okay, now that I've got everything factored. Now that I've got everything factored, now I can start canceling. I have an x minus 1, and please, I'm going to say it again. You can't cancel parts. You can't say, oh, here's an x and here's an x here, let's mark them out. They go together. The x goes with the minus 1. This x goes with this plus 2. This x over here goes with this plus 3. They go together in pairs. Don't try to cancel parts and not the whole part. X minus 1, x minus 1. X plus 2, x plus 2. Removable discontinuity. You're left with nothing on top. Don't put a 0, put a 1. Why? Because there's a 1 right there. You just didn't see it. You're left with 1 on top. You're left with x plus 2 times x plus 3 on bottom. Finished. As you write that down, I will tell you, if you graph this, you would have a hole at negative 2 because it canceled. You would have a hole at positive 1, and you would have a vertical asymptote at negative 2 and negative 3. Okay, that's, again, I'm getting ahead of myself, but if I kind of introduce it now, when you see it again, hopefully it'll stick a little bit better. Let's see how many more of these we got. This is the last one. Last problem of the day. Noah 2a minus 2b. How can I factor that? Pull out. Good. And I'm left with a minus b inside. Over 6. If you'd like to factor 6, go for it. You can factor it at 2 times 3 if you'd like to. You don't have to. 9a, if you want to factor that into 9 times a, that'd be fine as well. It's already linear. A squared minus b squared, Abby. Break that apart for me. A's. Perfect. Conjugates. Any questions about how she factored that? Difference of squares will always factor into conjugates. Now let's simplify. Now let me point something out. X plus 3 over 6. This is what I've been cautioning you about. You can mark out the 6 and the 3. That 3 has a plus attached to it. 3x over 6. You can mark out the 6 and the 3. Why? Because there's no plus or minus. Okay, if it's separated by multiplication, you can cancel part of it. If it's separated by addition, you cannot cancel part of it. Okay? Now these two things are separated by multiplication. I can cancel out an a minus b and an a minus b. And a lot of people would not want to cancel that 9 because they say, well, there's an a attached to it. It's by multiplication. You can cancel part of a multiplication fact, but not part of an addition fact. Okay, not part of a binomial or trinomial. So I can cancel out the 9 and the 6 and leave me with a 3 and a 2. That's legal. I reduced it. I can also mark out this 2 with this 2. And I'm left with, on top, 3a. And on bottom, I'm left with a plus b.